Hi there, welcome to Vectors 2. This is about the I and J unit vectors. So this is the first bit of really new A-level content that we're going to start today in terms of the vectors work. So we want to introduce this idea of a unit vector. Now, as kind of is suggested by the name, a unit vector is any vector that has a magnitude of 1. Quite often when we talk about unit or unity, we're talking about 1. So a unit vector is any vector that has a magnitude of 1. And by convention, we define two important unit vectors. There are more, and we'll see that in a later video, but we're going to focus on two important unit vectors. We refer to them as the I and the J vectors. And I've written them in column vector form there for you, 1, 0, and 0, 1. And clearly they have a magnitude of 1. And so we use these two vectors because these two vectors are at right angles to each other, which is useful for us. They also can be thought of as kind of a step each in the x and y direction, where I is in the x direction. So I is along in the horizontal and J is in the vertical. Now it's really important you learn which one is which and get used to that. That's a key thing. Okay, so I is going horizontally and J is going vertically. As we use them more and more though, that will become easier. So I and J are our two important unit vectors. And we want to know kind of why we use these really. So it's a convention and it's but they can be useful for us. And so if I have, for instance, any vector, I can use unit vectors. I can use these I and J unit vectors to write. Okay, and that allows us a kind of standardized form to write vectors, which is really useful. So if I have this vector A, I can use my vectors I, so 4 lots of I, and 2 lots of J, to give me a pathway, so it shows that A is 4I plus 2J. Okay, and this is the latest form of writing vectors, 4I plus 2J. So this is in the I and J form. Now, we can kind of see where I and J are 1, 0, and 0, 1, that if I do and substitute in these values, I get all the way back to 4, 2. Okay? 4 and 2, which as we can see in this vector, 4 across, 2 up. Okay. Now, this is a conversion that we're going to be using a lot, going from this kind of I and J unit vector form into column vector form. And we can see quite easily the coefficient of I is just our x component of our column vector, and the coefficient of J is the kind of y component of our column vector. Now, I'm going to give you a couple of questions to actually try yourselves here, just to double check that you're comfortable with that. So just an example, so as I've said, A equals 4I plus 2J, so A is 4, 2. And if I was going in the other direction, if I was given this vector G, which is 14, negative 2, it should be quite obvious to us that I can write G as 14I take away 2J, where I and J are my unit vectors. Okay. Now, I'm going to put, in a second, I'm going to put another few questions on the screen. I'd like you to pause, have a go at them. Once you unpause, I'll then put the answers on there for you to check yourself. So these are the ones I'd like you to convert. These ones into column vector form, these ones into I and J vector form. And these are your answers, so well done for getting those correct. If you didn't, have another go at them for me, please. This is a really important skill. Key ones are where we haven't got any coefficient. I don't need 0I, we don't need to write it, okay? And the same down here, 11I, just means that there's no J component. So, if we're comfortable converting between these I and J notation where we're using a unit vector into column vectors and vice versa, it makes our life much easier when we start using these I and J notation. Now, what that looks like could be like this. We're going to go through a couple of examples. If I'm told a vector A, which is 3I minus 2J, and a vector B, which is negative 2I plus 3J, I've got those two vectors and I want to calculate A plus 2B. Now, straight away, my first step, when I've got to do any kind of calculations with a vector in unit vector form, I'm actually going to put them in column vectors. It makes my life significantly easier. So A is 3, negative 2, and B is negative 2, 3. We should be happy with that now. I want to calculate A plus 2B, so I can substitute these in straight away. 3, negative 2 plus 2 lots of negative 2, 3, which gives me A plus 2B is 3, 2 plus negative 4, 6. I've obviously just multiplied this. That means a plus 2b is negative 1, 4. Now I've got to find an answer now, but by convention I'm going to give my answer in the form of the vectors that were asked of me. Okay, so I'm asked the question being given I and j vectors, and so I'm going to give my answer in the form of I and j vectors. So a plus 2b is negative I plus 4. If you've got negative 1i, that's fine. So we can still do our vector addition with I and j vectors, and it might not be that obvious why I and j vectors are useful necessarily, but having unit vectors does make vectors a really powerful way of doing calculations, and this you'd see if you took maths a little bit further, either in the applied or the pure side. Now we'll do one more example. This one is in 2 parts. Okay, so I've got vector A, which is 5i minus j, and vector B, which is negative 3i plus 7j. I want to find the value of lambda if a plus lambda b is parallel to the vector I. We're going to do part A first, and then we'll have a look at part B. Okay. So I know I've got A and B, and I've defined them 5, negative 1, and negative 3, 7. Again, we should be really quick at that. It should be nice and easy. So lambda is, I want to find the value of lambda if a plus lambda b is parallel to the vector I. Okay. So again, I've got this thing where it's like parallel to the vector I. I want to know what this is when it's parallel to the vector I. So I've got a plus lambda b, and I can write it using my column vectors. I've just substituted them in. 5, negative 1 plus lambda lots of negative 3, 7. Okay. Now if I think about it, if it's parallel to the vector I, that means my vector is only going horizontally. That implies that the component of j will be 0. Okay. It implies to me the component of j is 0. The only way a vector can be parallel to the vector I is if the component of j is 0. If the component of j is 0, that means that along the bottom here, my equation would equal 0. So I can write 0 is negative 1 plus lambda lots of 7. Because once I do this sum, once I calculate this, negative 1 plus lambda lots of 7, or 7 lambda, I know that needs to equal 0 to have no j component. That means it will be parallel to the vector I. And then I've just got a relatively simple equation to solve. So here in this case, lambda is 1/7. Okay. This is kind of a special case with parallel, when you've got a situation when it says that it's parallel to I or parallel to j. If it's parallel to I or parallel to j, it means that either the j or the I component will have a coefficient of 0, and you can use that special case. Now, in the second question, we've got a different kind of proposition. Now, this is mu, which is a different Greek letter. Okay, so it says the value of mu if mu lots of a plus b is parallel to the vector 3i plus j. Now, if we're told here, parallel to the vector 3i plus j, I know that I can write mu a plus b equals lambda, so some constant lots of 3i plus j. Okay, this is my definition of parallel. I'm just saying that it is parallel to this. I don't know what these values are yet, but that's what I want to try and find out. Now, I also know the value of a and b, so I can start calculating this. Mu lots of a plus b is mu lots of 5 take away 5 minus 1, plus negative 3, 7. Now, that means that I can substitute in these column vectors and kind of find some expression using this original kind of proposition, this original definition of parallel, and I get this. Mu lots of 5, negative 1, plus negative 3, 7 equals lambda lots of 3, 1. Okay, where 3, 1 is the column vector version of this vector. At this point, I've got 2 unknowns. Now, I can't obviously solve them with one equation, but luckily I've got coefficients, so I've got this kind of top line equation, so 5 mu minus 3 equals 3 lambda, and I've got a bottom equation, negative mu plus 7 equals 1 lot of lambda. That gives me simultaneous equations. Okay. Now all I've done is this is the top line, this is my I components on the top, and this is my j components on the bottom. I'm going to solve these two to find me my value of mu. Okay, if I've got two unknowns, I know I'm going to need two equations. Because I'm finding the value of mu, I'm going to substitute this second equation into this first equation. I want to eliminate lambda. Okay, just makes it easier. You can find lambda first and substitute in, but it's easier if you eliminate lambda. So I'm going to substitute the bottom equation into the top equation. So I get this, 5 lots of mu minus 3 equals 3 lots of mu negative mu plus 7, and at this point it's an equation with one unknown. It should be nice and simple to expand, simplify, and solve, and get the answer mu equals 3. Now, the step up, these two questions are quite difficult, especially the second question. It could be quite complicated. Have a go at the questions on the sheet. Revisit this if you need to. Good luck.